Good morning, everybody. It's my pleasure to present your speaker for Bressel from the University of Los Angeles. We will speak about on the signature of the modular funds. Okay?
Right. Thank you very much. Well, let's, I'll get into this. The talk, depends on as I said. Really work with my former master student, actually, in Gables. This, I had a political John Ranger. All right, well, so in like 2002, young who I don't know, and with China, so they who published a paper in New notice with a year and now right now kind of best case scenario version of that. So their statement is slightly somewhat more general, but it's easier to understand than how it's going to determine. The theorem is, so I take well, a fan which is complete. So simply solid. And you want it. I'll explain it for the words. The modular in particular means that it's rational. Of dimension, which is infinite. And to one of these corresponds for a variety of thinking more complex numbers. This is the correspondence. So using modular is like saying smooth. Smooth, complete. Okay. All right. So there is a condition on heat. So it's called local convexity. So if he's locally convex, I'll explain what that means. Then so such a smoothie, right? They have signature. Sure. Number and one can predict this sign. Depends only on the dimension. So quickly try to go through the terminology. Right, so, well, if M lives in the vector space, when we made, I'll call it V, and we think it's all right. So the fan there's a finite collection vex, and in this case, I mean it's three polyhedral cones. With the whole problem. So every cone has bases which are columns of local dimension. So we imagine that, so the two properties, one is a two columns intersect. It's and it's kind of complete in the sense that so if let's say I have a cone and I'll just write it like this. So now is a face sigma, so it's partially more than 7. Right, that value is less or equal to sigma. It's a face. So sigma is the face of sigma. The origin is the face of any cone. In particular, for any family, there is a minimal cone, which is the origin. So then, that is also this. And then there are these words here, which I'll make so simplicial. Simplicial, well, means that every cone is simplicial, which means that so one-dimensional cones are referred to as arrays. And so simplicial means that basically every cone has rays and the number of rays is correct, is equal to the dimension. So if so if you have any questions, please. So they're basically like simplicities. Yes, complete. So that means that the physical union, these cones are subsets of the vector space of all cones is all of the vector space. So it's basically the whole Rn into the symbolisms. So rational. Well, so one should kind of feel like these properties, these are geometric properties, and these are like arithmetic. This is which will become important at some point. So, well, you have a lattice inside of the vector space. And in general, you take all the vector space through the lattice and the rationality is with respect to the lattice. And what this means is that so what happens in that case is that every ray has a primitive vector. There's like the rational means that this vector. The ray passes through the lattice. Well, of course, what I mean, I don't mean that they all come out of the origin, which is an integral point. So maybe. One to stay in various ways. That's so important. So what happens is that in that case, every array has a primitive generator. It's the first integral, the shortest integral vector. Okay, so unimodular. So unimodular means this. So if I have, so for cones. So if I take the vectors of arrays. Read. Well, if it's sequential, we already know that the, well, non-zero vector is a array, so simply a part of the basis of the vector space. But in this case, they are part of an integral basis of the lattice. Sometimes it's stated in terms of volumes. So, for example, in R2, this is 1, 0, 0, 1, and then I add the third rate to make it complete. So for instance, -1, -1. So these are the rays. And these are the third rate cones, and in fan, this corresponds under this to the projective point. And indeed, in a pair, for instance, point the basis. However, if I change this vector a little bit, let's say practically anything else, it will not have this spot. But will correspond to the way to project the space, which is not necessarily smooth. Combinatorial, so this, however, will be the same. The partial order separate basis. So one has to distinguish a little bit between the combinatorial properties and properties involved with arithmetic aspects. Oh. Okay, so under the correspondence, so if we have a rational fan, then you have the variety, which I don't know if that's. So these words mean the poems of complete. Means complete. You want or means smooth. And other fans, not necessarily can be, we don't need to. go into that. And finally, there is this property called local convexity. So. Local convex, nothing to do with the lattice, means the following. So for yeah, the ray in the fan. So it has a star. Well, but here I mean I don't distinguish, it's only confusing between the space and the auditorial aspect. But it's physically the union of cones which contain this ray thing, right? So the star, the local convex for all rays, this is convex. It is well, so the theme, the subject is kind of implications of some convexity assumptions on positivity of certain numbers of combinatorial nature. So to appreciate what this means here, for instance, this is obviously not local convex. Is the star of any one of these rays is the union of the neighboring cones. And the problem is that there are not enough rays. So for instance, when I say convex here, I don't mean necessarily strictly convex. So here is another picture, which is like B1 times B1. So that is okay. Of course, it would have been even better to do like a half more rays. First, you might say that, this depends on the position of the rays. Well, because, for instance, this is also a fan of the same combinatorics, but it's not very good at this rate. Doesn't matter, because to us, so this is kind of interesting. But roughly speaking, from the combinatorial point of view, here, the condition is like enough rays. For the higher dimensions, I cannot even begin to imagine what it takes. Okay, so now what's left to do is explain about the signature. Yes. It easily, well, this is exactly like I said, well, in the case of straight. Local convexity, lateral needs to blow down the of the device. Right, because to blow down such a divisor, it means to erase the rate together with everything around it. So then you should have a convex cone left, which is what the conditions in the straight. And non-straight cases, where it's not exactly this, but slightly degenerate. Yeah, blowing down would mean that just which something I could do here or here, rather than just erase this. And this is still a convex cone. Okay, so signature. Are there any questions? The properties. All right, so what is meant here is that, well, we have this, the signature. So suppose I have an even dimensional. Manifold closed. We come back to our boundary and orient it. And let me assume, which this is true for 35 is, for instance, that. So it has homology, and I'll just write HX for short, you can develop, let's say, homology with real coefficients. You can substitute. And let us assume, to simplify the discussion, that the odd degree homology is trivial. Well, in that case, so you have the point character array. You multiply and integrate. So this means that so this defines on the symmetric bilinear form, non-degenerate. Has the signature. So what I mean by this number signature of one right there. So a couple of remarks. So let's say the dimension is, twice n. The meaning of n will change. This is local notation. So first of all, if n is odd, then this number is automatically 0. Because it's hyperbolic. Now if n is even, well, in that case, what happens is that you have the middle degree homology. Maybe like degree 2. And so then this same number is equal to the number of obtained by taking one character and restricted to the middle degree column. This I'm discussing this under this condition. Where there's no odd columns. This factors. And sometimes you find the definition of signature or manifold whose dimension is divisible by 4, and then it's given like this. There's no reason why not to include all the rest. And for us, it's maybe useful. Okay, So I have any questions? So this is the number. I mean, for signature is limited there, has wonderful properties and so on. But this is interesting because some condition predicts the sign of infinite family. So I will not try to avoid the geometric side of this. You would clarify this. But let me just say a couple of words about the strategy of the proof with products and the our tiny contribution is to this. Well, it's roughly like this. So first of all, there's Gibson-Blue signature here. Gibson-Blue says that this signature is some integral of some characteristic class. Will come in, but important. So then, so this is a function of the pentagonal classes of the manifold. So there is only hope of there something non-zero only in the case when the dimension is divisible by 4. All right, so then so now well, one even dimensional example would be a complex manifold that's automatically three-dimensional, like in our situation. And so you do a calculation with characteristic classes, which will come up in the more combinatorial version of this, but the point being that, so this will imply that in our case, by our case, I mean, theoretically, there, that, for instance, the signature is, well, it's the alternating sum of H numbers. But here I have a feeling, these indices here, there is no -1. The fact, these are 0, 1, 2, 3. I mean, we previously were phase numbers of a superficial complex. But on the fan, all of those dimensions go up by 1. So there is no -1. It's 0. The orbit. Okay. So this is a strange compound. I'm not a professional combinatorist. Does this come up? It does. Alternating sum of H numbers. This is not the Euler characteristic. That would be the sum without signs. All right. So anyway, in the complex case, so what happens is that the same number can be written like this, which is given by this formula. So it's the integral B L class. And of course, only its part in degree maybe I should say, and this is it's so good with respect to this. So let's say dimension of phi is n. Or sorry, 2n. An even dimensional n, in which case x phi has a real dimension divisible by 4, so which is 4n. It's this integral, and one can calculate like some of the characteristic classes and find out the form. Roughly speaking, minus 1 to the n times this integrand looks like this. Right, so the partition n in positive, numbers will be minus 1 to the k times some positive constant, not so important for the sign issues, and then there will be a product of, well, basically each array that responds to a divisor on the Doric variety, in other words, a class of degree 2 in cohomology. So this monomial of these classes has degree 4n.
The sum under there,
This is so it's the sum over the decompose n into non-zero positive, strictly positive numbers, and you get the corresponding monomial. So there is a sign which depends on the number of factors. It's k. Then there is a big number involved, Bernoulli numbers, and who knows what, but it's positive. And then there is this. And the point, and what those are the arbitrary. No, these are homology classes. Each array corresponds to a degree 2 cohomology. Follow this. For the class, I guess it's star.
So what it is for each. Index, we have one rate.
No, we take all rates. Yeah, all rates. So, yes, so who are these? Row I. Row I are all rates. Yeah, so it's a big sum. I took all rays and my number. For one, or whatever they do. But the point is that in this, well, so what happens is that, well, basically, one has to compute the integral, or if you like, those intersection numbers, and the point is that this condition implies, after a little thought, that, well, all these terms are positive, basically. There's no cancellation, there is all positive numbers. All such products individually are probably let's say, not like.
Was, is this something they discovered or was this?
I think, with this expression, this is this characteristic class computation. So, on a complex manifold, we can re-express. I will come back to the combinatorial version of this, so it's easy for you to translate between the two. One can rewrite the L class in terms of Turing process. Well, right, it's not like that much going on. I think there's some look thoroughly.
So they just rewrote the code line for the right.
Oh, yes,
Yeah.
there is a signature theorem for the very variety, but then, so, I mean, there's some countless considerations involved. And, it just comes out positive, automatically. I guess, if it's strictly convex here, then this literal is a positive number. Unfortunately, that's really almost it cannot happen in prior communities. Okay, yeah, so what is very quickly, I see. Little time left. So what is our 2 cents on this issue? So one would like this, so first of all, one knows that one can define signature very generally, because one has homology with real coefficients. Just 3 out of the fact. Together with all these features, and it's equal to this for a rational fact. One would like to basically eliminate rationality from all of this. I mean, the statement is combinatorial. Unfortunately, well, rationality, it's not just rationality, it's meaning modularity. So you lose the distinction between, it's like the singular, their theorem, in principle, is supposed to serve as, not just unilateral events. But then one needs slightly more powerful than this.
But they talk about or the definition for all.
No, that would be non-simplicial. Okay, so in that case, I don't think one even knows. But one wouldn't know how to state the condition. Local convexity in the non-simplicial case is, I don't know what the generalization should be. But that's fine. But if you lose rationality, you lose this condition, which is unfortunately I don't see a way to do this. So all we try to do is eliminate the correct variety from this complete. Well, correct variety is actually a space threefold. Vector bundles on the side of the tangent bundle. So this doesn't seem to be completely obvious, okay? Yes, so the goal is like, well, so you eliminate the correct variety. But like I said, with the golden principle of losing the rationality assumption, which makes a lot of sense. Now, I cannot believe that general fans, which are simple, can be the locally complex, exhibit behavior different from this. But I'll be prove it the same in other story.
Is that what looking and that's not
No, right. No, well, I explained maybe, hopefully, let me, what the difficulty is, it will become, so here's the plan, I'm sorry. Yeah,
not right.
so first of all, I mean, there are obvious difficulties. Yeah. So first, what is signature? Well, if you have a fan like this, or like I said, theme is a complete simplicial. So where does the rationality enter? That's complete simplicity. at a certain moment, but up until that moment, it's all good. Right, so signature, well, we have homology of heat, whatever that means, which is, of course, equal in the rational base to all of the together with all the structures. So let us say, but there is a little change of grading compared to what you do, people in the Combinatorial. So this HI is dimension of H2I. Or in the language used previously, what you call linear functions, they have degree 2, which is more natural for various points of view. Okay. And so signature, so then we have well-defined signature. Which coincides in the rational case with those numbers. Yeah. Okay. Then 2. Now, well, I cannot explain this, okay, but basically this equality has to do with this calculation, observe what comes out, but in our case, what this means is the following. So we have a representation, I call them sheaves on representations of the pulsate field, or the opposite. Like, so there are various states, but there are these combinatorial differential forms. So to give such a very quickly, to give such a representation, it means that I have a vector space for each cone, and the vector space is this. The cone sits inside of the vector space, and its annihilator in the dual space is a vector subspace. So the functionals which vanish from sig. So I'll just write this. The dual space of them. Now, if you have if this cone is smaller, then the annihilator is bigger. Right? So you have, I mean, there is an inclusion, really. And this is obviously transitive and whatnot. And sheaves have homology. Also, there are other theories. Then you put omega I is I is the exterior power of omega 1. Now, group is having anything to do with, say, forms on the periphery. It's a philosophical question at this point, which we're not going to answer. However, one knows the following is easy. So you can have chief homology. And chief homology. And if there's only can I not write that anymore? Chief homology here is 0 if I is not J, and its dimension, and if there is a canonical isomorphism. This is not homology with constant coefficients, by the way. Just like in the direct work. Now, there is a little problem. We don't have fit to Brooks theorem in mass. So this equality is not which used to be a consequence of Brooks theorem, and I don't know of any other reason.
Well, this is a particular simple case of some slightly more general statement for any complex manifold. No, why it's true, geometrically speaking, no idea. As it stands, it's a formal computation with characteristic classes. So in other words, we have to prove a theorem directly. It says that signature of P is the alternating sum of H numbers, which are dimensions of this. This can be proven directly, so to speak, by geometric methods. Now, this number, if you think in terms of Euler characteristics, is like this, because this is, there are signs here which are compensated by the degree. So in the end, it's sum of Euler characteristics of these sheets. Well, I mean, it's not much of a Euler characteristic, it's almost only 1 degree, but with an appropriate sign. Oh, okay, so now we are like doing 31 rock here. But for what? I mean, I'd like to calculate this by intersection here. This is the only way which leads to some understanding of science. If you have any experience with it, right? You conjecture something, some finer facts. I mean, there is nothing. Why some number? Oh, by the way, yeah, you can replace this number. Well, the sum is an alternating sum of some positive numbers. And I mean, for a polytope, it would follow from quadrennial bilinear relations with equality. But in general, I mean, who knows? Nevertheless, it's true. And I can predict this sign. Amazing. Okay, so Riemann rock looks like this. So you form the Grothendieck group of sheaves of finite dimensional real vector spaces on phi. Then, well, we have this cohomology, which is finite dimensional. But before that, there was something better, and that was, well, oh, sorry, phi. I'll just write this. But what this is the ring of continuous piecewise polynomial functions previously mentioned without continuity, which should have been there. Right, so on each big cone, you have a polynomial and they agree on common faces. And this map is a reduction modulo the global polynomial of without constant term. Here's a surjective map. Well, this is an algebra over global polynomial, which were continuous polynomial functions in effect. And you reduce mod the ideal of the origin. You get a finite dimensional graded vector space, and this is it.
How do you find there at the beginning each of the path?
Well, like,
Do you define it?
well, there are many ways to calculate that. This is the same as standardized range, is just the same as anything you want. Or you can sum these and take it to the definition. Spaces can go up this, and there are these spaces called the space of Minkowski weights. Where I think that there is a, if they're not equal, there is a very, very like, close relation. Yes. Yeah, so it's, me personally, I like this, but you know, Stanley Reisner follows from this understanding very quickly. Right, so we construct Well, there is this Chern character, like equivariant Chern character, whatever that means. And so it's composition with projection. Well, how do you define that? Well, this has a basis, which is this. I'll write it, I'm sorry. So there is this, the constant sheaf, one-dimensional. And then for any array, you have, well, that constant sheaf, and it maps to the, well, the structure, sheaf of star overlay. Arrays. Right, and you take a kernel of that, and you call it O of rho. I think this is what you would call O of minus zero in algebraic geometry. I would prefer zero O, but it is just all this. It's like the ideal sheet. And then in general, you go O sigma, you take the rays of sigma. And you just multiply these literal. Let's face it. And this actually was a basis, three bases, and you just give formulas for this. Namely, I'll just say this in words. So these formulas, they are just like what you would do in algebraic geometry or topology, except that the first term class here, the function, is given by this piecewise linear function mentioned previously, which is 1 on the primitive vector on the array and 0 on everything else. And you just write the exponential. Right? But, how you feel about this in topology. In topology, this is about topological key theory and topology, and this is the map of rings. Here, it cannot be a map of rings. The tensor product here is ridiculous. Nevertheless, this works. This works when you take tensor products of these line bundles where rays are distinct. It's amazing that.
So it works in the sense that
If you square your, if you square this, you get basically the same thing. Because R tensor R, and square is R. This is a characteristic function of something. The degree is not known here. It's all different. So how to normal? And this is where we come to this unimodularity. This is where you need a unimodular family to have a proper normalization for this. And if you don't have it, you try it, this magnetic approach doesn't work. By the way, the formula for characteristic classes, and we do it all on the non-unimodular superficial family. I mean, let's say dollar classes, but the man is a complicated formula involving things which are not visible. You're right. We lost the lattice. So we turn the lattice on only for this to work. And then we'll move the one rocks here, which says that this number, the H number, or the Euler characteristics of any sheet, and in particular these, which are computable, are integrals over the fan of something, and you'd be surprised. So you write it out, and it looks just like this, with these functions in place of these. And a little argument this is fulfilled because basically instead now it boils down to the fact that some mixed volume is positive. I think it's time for me to
audience for today? Are there any questions in the audience or the general audience?
So that this also general, there is a version of. You drop the modularity and talk about. They
use some. How you wrong, or somebody. And how us, outside is better. The remark and the cohesion is. Well, formally, the most just like this. You might ask, you might ask, what does this mean physically? Well, if you take, the first thing first, we mentioned this n equal to 1. In the plane. But 2 is 2, right, in the plane. Well, if you want this in the color from the signature, you need to have at least 4 rays from this computer. So it makes sense. You want strict inequality, you have to have at least 5 rays. I propose this as an exercise, and it's a direct calculation. This she's still over there. Vector spaces which are sometimes 2 dimensional and usually 1 or 0 dimensions for this whole number is easily computed. So in higher dimensions. But it is kind of free. Supposed to be related to some other conjectures, the authorities. Or something about regulations is here. Thank you very much.